Hi everyone, if you're new here, my name is Ryan, and today I'd like to solve this FE fluids problem with you guys. You can try this problem using the first link in the description below. It'll take you to this screen where you can solve this problem interactively for free, as well as all the other problems that I've done in my FE exam playlist. On your upper left, you can see this flag question button. That's how you can access all the other questions, as well as you can input an answer, and if it's wrong, you can go ahead and read the explanation. It'll link back to a video solution like this. You can also read the written solution with explicit references to the current FE reference manual. Now, once you get the right answer, you can go ahead and input it. You can move on to the next question. And yeah, so I recommend you go ahead and solve those problems just to get a quick refresher on some of the concepts on the FE exam, as well as it's free. So yeah, go ahead and give it a try. Okay, let's get back into the video. It says a green rectangular gate with a depth of 2 meters is submerged in a body of water and is shown above. The gate is pin connected at its upper edge and is in smooth contact with the ground at its lower edge. The reaction force exerted by the ground onto the gate is most nearly. Now for this problem, what we're going to do is employ something called the pressure prism method. And it's a more first principle kind of method. And these first principle methods are really good because you don't have to waste time in the FE reference manual. The less time you spend in the FE reference manual, the more you get to actually focus on the problem and the actual problem solving process. So that's what we're going to use today. Not only do you have more time to solve the problem, additionally, you get to review different concepts from previous topics because those first principles are all connected between all the different topics. You're going to see in this video, we're going to review concepts like distributed loads, centroids, different concepts from calculus, like integration. And yeah, it's a much more powerful method in terms of retention, which a lot of people struggle with. If you employ these first principles, what you do is you're able to retain more information. Ensure you keep using the same concepts over and over to solve multiple different questions and bring all those concepts together. So that's what we're going to do today. Let's start by writing down some of our givens. Firstly, it says we have a depth. The gate depth is 2 meters. That'll be kind of this dimension here that I've shown on the cross section. We also see here that it's inside a body of water, right? The density of water is 1,000 kilograms per cubic meter. That's something that I would memorize because it's commonly used on the FE exam, and it's not always given. Additionally, very important to these kind of problems is the fact that the pressure at any point inside of a fluid, inside of a static fluid, is governed by this kind of principle of hydrostatics, which is that the pressure is equal to rho gh, where rho g, that's the density times the gravity, is also a specific weight, right? That's the product of rho times g. So gamma times h is the pressure at any point inside of a static fluid. And on the left side, that's a static fluid, right? It's exerting some pressure onto that gate. And if we were drawing a free body diagram, it's essentially a distributed load on that gate. Now it says that it's pin connected at its upper edge and that it's in smooth contact with the ground at its lower edge. With some of this information, we're able to go ahead and begin constructing our free body diagram. We have a horizontal reaction, that's AX, as well as a vertical reaction, AY. It's a pin, so it'll have that constraint in the horizontal and vertical direction. We have a normal force exerted perpendicular to the floor surface, so that's why it's fully vertical. And we would have a friction force, but they said it's in smooth contact here, so we don't have friction. Additionally, there's different pressures acting on this gate at this kind of 5 meter kind of depth. This point here, as well as this point here, it has a pressure equal to 5 gamma. And all the way at the bottom, we have a pressure equal to 8 gamma. Pressure acts to compress the surface of this gate. Its magnitude at the tip of the gate is 5 gamma. And all the way at the end of the gate, its magnitude is 8 gamma. Right? That was from that principle of hydrostatics that we just kind of spoke about. Pressure is a compressive force, so it's kind of pointing inward into that gate. And really, it produces a kind of distributed load. The important first principle is that once we have this free body diagram that we've drawn, where we realize that the pressure is acting perpendicular to that surface in a compressive format, and that bottom portion is just a normal force, it's smooth contact, so there's no friction force. What we can do is take that pressure and use it to produce a force. A pressure is just a force per unit area, or we can also say that a force is just a pressure times an area. Now, this is true if the pressure distribution is flat, it's uniform across the surface. But if it's not, then what we could do is integrate that pressure with respect to the differential area. Now, that looks complicated, but the truth is that all we're doing is taking a little differential area and raising it up to the pressure. Once we raise it up to the pressure, we essentially get geometrically an area shown on the screen, but once we expand it through the depth, we get a volume. What that means is that after we add up all of these volumes, we're able to compute a force. The takeaway is that geometrically, when you find this volume under the pressure distribution, what you're computing is a force. So if we just wanted to go ahead and draw this free body diagram. Okay, so shown on the screen here is that free body diagram that we drew on the left with the pressure distribution. And what we're going to do is think about, we split these forces, think about how we can split the pressure distribution to produce forces that we can compute and we know where their centroid is. Now you can see I just drew a black line here. I split it up into a rectangular load and a triangular load. And these are both prisms because they're constant in the thickness. For the rectangular load, if we think about the volume under that distribution, its height is 5 gamma and it's acting over an area. The area is just this length here times 2. What's the length of the gate? If we go back up to this upper kind of surface here, this is the difference between 5 and 8. It's 3. Using the information from this 3, 4, 5 right triangle, we can see that the gate length, this side here, is equal to 5. So we have what the gate length is. The gate length is equal to 5, and the gate depth is equal to 2. 5 times 5 is 25, times 2 is 50. This is 50 gamma shown here, and this is due to the rectangular load. We would place it at the centroid of the distribution. That's L over 2 from the tip. We'd also have a contribution due to that triangular load. And the area of that triangular prism, this height here, is 3 gamma. 3 gamma multiplied by the base, which is 5. It's a triangle, so we have base times height divided by 2, multiplied by the depth. It's a 2-meter depth. This is 15 gamma, and we place it at the centroid of the distribution. That's L over 3 from that bottom edge. If we're looking for that normal force, which this is exactly what we're looking for in the problem, we can sum the moments about point A and make sure that we get a 0 value. What that means to me is that once we go at point A, those two forces won't produce a moment. They have a 0 valued moment arm. And we'd have the two contributions that are clockwise. That's one due to the 50 gamma with a moment arm of L over 2. We'd also have another clockwise contribution due to that 15 gamma that comes from that triangular load. It's not L over 3, but it's the complement of that 2L over 3 from that A point. That must be equal to the normal force multiplied by that moment arm. You can see the moment arm here, the perpendicular distance between A and N is not L, but L cosine of theta, where this is theta here. And from that similar triangle, what you can kind of read off here is that cosine of theta is equal to 4/5. So remember that that's L cosine theta is the moment arm. That's just L multiplied by 4 over 5. If you're enjoying the video thus far and you're finding it useful, please leave a like and subscribe. It really helps me out a lot and lets me know that you're enjoying the content. Let's get back to the video. This is equal to 35 divided by 0.8. That's 43.8 0.75 gamma. If we go ahead and plug in for this normal force, what is gamma equal to? Gamma is just equal to density times gravity. Density times gravity. The density of water was 1,000 kilograms per cubic meter times 9.81 meters per second squared. That's just 9810 newtons per cubic meter. We take that and multiply by 43.75 to get a value of 429,187 newtons. Or what we can say is that's 429 kilonewtons. So let's go ahead and check that answer. Make sure we're correct. So right here, we got a 429 and we got that correct. If we go ahead and view the explanation here, what we see is that I've outlined two different methods inside of the solution. You can see the first method is where we just use those formulas, and those formulas would be on this sheet of the reference manual. So you can go ahead and look through that solution if you're interested, or it'll be good practice to kind of practice the formulas if you'd like to do that. But more powerfully, what we did in this video was we used the first principles. The fact that if we want to compute a force, that's just the integral of pressure times the differential area, kind of add it all up. Geometrically, what that means is that this is just a volume, right? We have a volume of a rectangular prism that we could compute and place at the centroid, that L/2 point. We also have a triangular prism. That triangular prism we placed at a distance L/3 from the bottom surface. Once we placed those forces and find those volumes, we took a moment about point A and we were able to compute that the normal force was equal to around 429 kilonewtons. If you enjoyed the video, please go ahead and leave a like and subscribe for more content like this. Thanks for watching. I'll see you in the next video. Goodbye.